Hello there. A very warm and a very quiet welcome to the Midnight Scientists. I am so glad that our paths have crossed here in this peaceful space, in this moment suspended between the day that was and the night that is to come. Wherever you are, whatever kind of day you have had, I invite you now to let it all go. Allow the weight of your body to sink a little deeper into the surface beneath you. Feel the gentle rise and fall of your own breath, a quiet rhythm that has been with you all along. Tonight, we're going to embark on a quiet stroll, a gentle wandering through the subtle, soothing mathematics of the natural world. This is not a world of stark equations or difficult problems, but rather one of soft, repeating whispers, a hidden code that nature uses to write its most beautiful poetry. From the impossibly perfect spirals you can trace in the heart of a sunflower to the intricate, self-repeating branches of a winter tree, and even in the frothy, beautiful chaos of a passing cloud, we will uncover how the world around us seems to hum with these hidden patterns. It is a world where numbers are not cold and rigid, but gentle guides that show a leaf the way to unfurl. It is a world where great storms swirl across the oceans with a secret and profound symmetry, and where even the lazy, meandering path of a river has a quiet geometry flowing just beneath its surface. Now, I should offer a gentle warning. This journey might be just interesting enough to keep your brain softly, quietly curious. If you find yourself lying awake in the dark, pondering the precise angle at which a pine cone arranges its scales, I can only offer my sincerest apologies. But then again, if you are to lose a little sleep, let it be in the noble and peaceful pursuit of understanding why a simple fern looks like a piece of living, mathematical poetry, a perfect thought expressed in green. Before we venture too far, if you find that this slow and curious journey brings you a measure of calm, may I kindly ask that you consider giving this video a like and subscribing to the channel. It is a small gesture that helps more sleepy seekers of knowledge just like you find their way to this quiet corner of the world. And if you feel so inclined, please let me know in the comments where in the world you are listening from tonight and what time it is for you in this very moment. I always find it so wonderful to imagine how far these quiet evenings can reach, connecting us all in this shared stillness. So please, snuggle in a little deeper. Let the day and all its concerns fall away behind you, like a single autumn leaf letting go of its branch to drift down onto the surface of still, quiet water. There is nothing left to do now, nothing to solve, nothing to hold on to. There is only the gentle current of this journey as we drift through the calm, quiet beauty of numbers in nature. And just a gentle reminder before we begin, this video is created for educational and relaxation purposes only. Now, let your breathing find its own slow, easy rhythm. Let your mind begin to soften. Let us begin. Let us begin our journey with something you have likely seen 1,000 times before. Something so common it is easy to overlook its quiet genius. Let us begin with a sunflower. Picture it in your mind's eye. You have surely admired its bright, brilliant yellow petals like rays of sunshine captured and held in place. You may have noticed its wonderfully sunny disposition, the way its face seems to follow the light across the sky. Perhaps you've even admired its tall, proud stance in a vast summer field, a sea of golden heads nodding gently in the breeze. But have you ever paused to stare into the very center of a sunflower and truly looked? Not just a passing glance, but a deep and curious gaze, the way a child might look at a seashell held in their palm for the very first time, tracing its curves and textures as if it holds some great secret. If you have, you may have noticed something odd, or rather, something oddly perfect. The dark seeds packed into its great round face are not scattered about randomly, nor are they simply crammed in as tightly as possible like marbles in a jar. No, they follow a pattern, a precise, swirling, mesmerizing dance of intersecting spirals that mathematicians and artists and nature lovers alike have come to recognize as one of nature's most elegant and persistent signatures. This pattern is born from something called the Fibonacci sequence. Now, please do not worry. We are not about to descend into a world of complex equations. This is not a lecture, and I can promise you there will not be a quiz. But there is a fascinating and wonderfully simple number story hiding at the heart of this perfect pattern, and it is a story worth telling. The Fibonacci sequence is, at its core, a simple series of numbers. It begins with 0 and 1, and each number that follows is simply the sum of the two numbers that came before it. So it begins 0, 1. Then 0 plus 1 is 1. 1 plus 1 is 2. 2 plus 3 is 5. 5 plus 8 is 13. Then comes 21, 34, 55, and so on, stretching out towards infinity, one simple step at a time. It is simple enough to explain, is it not? And yet, from that profound simplicity, a world of complexity and breathtaking beauty springs forth, a pattern that stretches from the smallest blossom to the grandest designs in the cosmos. Let us travel back in time for just a moment to meet the man whose name is forever tied to this sequence. He was an Italian mathematician from the 12th and 13th centuries, born Leonardo of Pisa, but he is known to history as Fibonacci. He didn't truly invent this sequence. Its principles had appeared in Indian mathematics centuries earlier, linked to the rhythms of Sanskrit poetry. But it was Fibonacci who introduced it to the Western world in his book Liber Abaci, a title that sounds like a magical spell, but was in fact a very practical manual on calculations for merchants. And in this book, hidden amongst chapters on bookkeeping and currency conversion, Fibonacci posed a curious thought experiment, a question about rabbits. He asked his readers to imagine a single pair of rabbits placed in a field. He wanted to know how many pairs of rabbits would be produced in 1 year with two simple rules. Every month, each mature pair of rabbits produces one new pair, and a new pair becomes mature and able to reproduce after its second month of life.
Yes, rabbits. It seems an unlikely place to find a universal mathematical key. But as it turns out, this fluffy, hypothetical puzzle of multiplying rabbits yields, month by month, the numbers of the Fibonacci sequence. And from that simple, earthy problem, things begin to spiral outwards, quite literally. Because those numbers do not just sit quietly on a page. They seem to breathe and live within the very structure of the world around us. In our sunflower, for example, the seeds are arranged in two sets of spirals that radiate outward from the center. One set curves clockwise, and the other curves counterclockwise. And if you take the time to count them, you will almost always find two neighboring numbers from the Fibonacci sequence. You might count 34 spirals, gracefully curving in one direction, and 55 spirals crossing them in the other. Or in a larger sunflower, perhaps you would find 55 and 89, or even 89 and 144. The numbers change, but the relationship remains wonderfully, peacefully consistent. But why? Why does nature do this? Is the sunflower a secret mathematician counting its seeds as they grow? Well, not quite. The real explanation is even more elegant, grounded in the quiet logic of physics and the patient work of evolution. A plant's goal is simple: to pack as many seeds as possible into the head of the flower, ensuring each one has enough space to thrive. It is a problem of optimization. Too much overlap between seeds, and you waste valuable room. Too little, and you are not using the space efficiently. The solution nature discovered lies not in the Fibonacci sequence itself, but in its very close cousin, the golden ratio, which gives rise to something called the golden angle. This angle is an irrational number, approximately 137.5 degrees. When a plant produces a new seed, or a new leaf, or a new petal, it places it at this specific angle from the previous one. Imagine you are placing tiny dots around a center point. You place the first one, then you rotate 137.5 degrees and place the second. You rotate another 137.5 degrees and place the third. What emerges is a pattern of perfect packing. Because the angle is irrational, the pattern never repeats. No new seed ever grows directly on top of an old one. Instead, each new seed fits perfectly into the neatest, most efficient gap left by the ones before. That is what sunflowers do, and it is what pine cones do when they arrange their scales. It is what pineapples do with their diamond-patterned skin, and what the petals of an artichoke do as they curl around its heart. They do not try to form Fibonacci spirals. The spirals are simply the beautiful, ghost-like pattern that emerges as a side effect of following this deeply efficient rule of growth. It's like a perfect natural traffic system where each new car follows the exact same turning pattern, and as a result, the entire flow of traffic arranges itself into a state of perfect, unjammed harmony. The result is order that is disguised as beauty, or perhaps beauty that is the inevitable result of perfect order. This golden angle is derived from the golden ratio, a number that has fascinated thinkers for thousands of years. It is often represented by the Greek letter phi, and its value is approximately 1.618. Like pi, it is an irrational number, which means its decimal points stretch on forever, never repeating, never settling into a simple pattern, a quiet, endless hum of digits. It is said that if you take any two successive numbers in the Fibonacci sequence and divide the larger one by the smaller one, your answer gets closer and closer to the golden ratio the further along the sequence you go. This mystical seeming number appears with suspicious frequency throughout art, architecture, and the natural world. It has been found in the ancient proportions of Greek temples, in the composition of Renaissance paintings, and some say even in the very proportions of the human body. The length of your arm compared to your hand, the joints of your fingers, the structure of your face. Many of these relationships hover near the golden ratio. It's not a strict, unbreakable rule set in stone, but it shows up just often enough to make you wonder, to make you feel a sense of connection to a pattern far older and larger than yourself. Back in the natural world, the beautiful spiral shells of the nautilus are often presented as perfect examples of the golden ratio in action. And while this is a slight simplification, Many natural spirals are what are known as logarithmic spirals. The principle is the same. A logarithmic spiral grows outward at a constant angle, meaning it gets wider but keeps the very same shape. The golden spiral is just one very special type of this spiral, and while nature may not hit that exact value every time, it often gets close enough to make you pause and raise a curious eyebrow. And here's a deeply calming thought to hold on to as you rest. This pattern-seeking behavior is not just something that our human minds impose upon nature. It is something nature does all on its own. The spirals, the ratios, the sequences, they are not mere decorations. They are tools. They are solutions to physical problems. When a sunflower packs its seeds with such impossible precision, or a pine cone arranges its scales into a perfect spiral, it is doing so in the most efficient way possible, given the constraints of its space, the nutrients available, and the unshakable laws of physics. These are not just pretty designs. They are living, breathing mathematical adaptations. It is a profound reminder that beauty and function are not separate things in nature. They often walk hand in hand. The world is not just beautiful for our benefit. It is efficient. It is optimized. And it just so happens that for us, optimization often looks and feels breathtakingly beautiful. Perhaps we have simply evolved to find these optimized patterns beautiful because they're so central to the story of life and survival. You can see these Fibonacci echoes in the delicate branching of succulents and in the swirling arms of a vast hurricane. Even the great spiral galaxies, spinning in the silent darkness of space, seem to nod gently to the same numerical ideas that shape a single flower. That might be a coincidence. It might be what scientists call an emergent pattern. Or it might be something deeper still. Some strange, quiet, cosmic rhythm that binds the tiniest seed on Earth to the vastest, most distant star. Now, it is worth noting, with a gentle whisper of scientific honesty, that our human minds are wonderful pattern-seeking machines. Sometimes we see these sacred numbers where they do not truly exist. The golden ratio and the Fibonacci sequence have been supposedly found in everything from stock market trends to ancient pyramids, and many of these claims are a bit of a stretch. It is a bit like seeing familiar shapes in the clouds. We are so eager to find structure, so comforted by it, that we sometimes impose the pattern after the fact. It is part of our human need to make sense of the world. But even allowing for a touch of this wishful thinking, there is no denying that the sequence shows up in the biological world with a frequency that is far beyond mere coincidence. And yet, for all of this breathtaking mathematical elegance, a plant does not know math. A sunflower does not count its seeds. A pine cone does not solve equations. What they do is grow. They grow according to the simple, unbreakable rules of physics, chemistry, and biology. And those rules, it just so happens, favor certain numbers and certain angles because they are the most efficient. The Fibonacci sequence is not the cause of this beauty, but the result. It is a pattern that emerges peacefully and naturally from a few simple rules applied over and over and over again. And when you truly think about it, that idea is rather reassuring. Nature does not need to be told what to do. It does not require complex instructions or detailed blueprints. With the right conditions,
And with the patient gift of time, order arises from simplicity. Spirals emerge. Seeds find their perfect place. Everything moves outward in elegant, efficient, silent loops. There is something deeply peaceful in that knowledge. In a world that so often feels chaotic, complicated, and rushed, the idea that a sunflower quietly follows a centuries-old numerical sequence just to make the best possible use of space is a kind of quiet, profound wisdom. It is nature's way of saying, slow down, trust the pattern. Everything has its place, even the spirals. And as you allow yourself to settle deeper now, deeper into rest, it is comforting to imagine that even in sleep, your body follows its own hidden rhythms. Your breath, your heartbeat, the slow, gentle dance of your thoughts as they begin to drift, all are part of a greater pattern, one that you do not need to control, one that has been unfolding since long before you were born, and one that, much like the perfect spiral of a sunflower, carries on quietly, beautifully, without ever needing to ask why. Now, let us leave the sunny field and wander somewhere shadier, somewhere cool and green. Imagine you have found a fern growing in the damp earth at the base of an old tree. If you were to gently hold one of its leaves in your hand and look closely, you might notice something truly curious. The fronds, those large, arching, leafy branches, are made up of smaller fronds that branch off from a central stem. And if you look closer still, you will see that those smaller fronds are themselves made up of even smaller, nearly identical versions of themselves. It is as if nature took the blueprint for a single leaf, shrunk it down, copied it a dozen times, and then artfully glued the pieces together to create a larger version of the very same thing. And then it did it again and again, in layers of repeating perfection. This beautiful, recursive idea, this pattern within a pattern, is what the world of mathematics and natural design calls a fractal. A fractal is a shape whose parts resemble the whole. It is a system built on self-similarity, which means that whether you zoom in or you zoom out, you continue to see a structure that looks remarkably like the original. In the case of our fern, each small leaflet looks like a tiny, perfect fern of its own, nestled into the larger architecture. If you were to stand on a rugged coastline, you might see the same jagged, irregular curves, whether you're looking at a few meters of rock or a few kilometers of shoreline. And if you have ever been lucky enough to see a Romanesco broccoli at the market, one of those bright chartreuse green vegetables that looks like it came from another planet, you have seen one of nature's most perfect fractals on your dinner plate. Each of its spiral towers is made of smaller, identical spiral towers. What makes fractals so utterly fascinating is that they seem to live in the space between perfect order and complete chaos. They are not perfectly regular, like a neat grid of squares, but they are not completely random either. They possess a kind of rough, organic symmetry. You can always recognize the underlying pattern, but it never repeats in the exact same way twice. Fractals are nature's way of being precise and wonderfully messy all at the same time.
Now, mathematically speaking, the idea of fractals was given its formal shape in the 20th century. But like so many beautiful ideas, these patterns existed in nature for eons before we humans finally found a name for them. The term fractal was coined by the brilliant and unconventional mathematician Benoit Mandelbrot in the 1970s. He was a thinker who saw patterns where others saw only roughness and complexity. He was studying a seemingly simple question: how long is the coastline of Britain? It sounds like a question with a straightforward answer, but the deeper Mandelbrot looked, the more slippery the answer became. Imagine trying to measure it. If you take a very long ruler, say 100 kilometers long, and lay it end to end on a map, you'll get a certain length. But with that large of a ruler, you miss all the little details. You skip right over the small bays and inlets. Now, try again with a shorter ruler, perhaps 10 kilometers long. This time, you can follow the curves more closely. You measure into the mouths of harbors and around small peninsulas. And as you do, the length you measure increases. Now, imagine using a 1-meter stick. Suddenly, you're on the beach itself, picking your way around every single rock, tracing every tiny nook and cranny in the cliffside. The closer you look, the more coastline there is to measure. The length, in a very real way, seems to depend entirely on how closely you are willing to look. It approaches infinity.
This strange, wonderful property that the detail and complexity grow as you zoom in is the very hallmark of a fractal. Mandelbrot took this mind-bending idea and applied it to a vast range of patterns he saw in the world, showing that so many natural forms could be described using this new language of fractal geometry. The shapes of clouds, the jagged peaks of mountain ranges, the delicate branching of blood vessels, the chaotic forks of a lightning bolt, all of them have this self-similar, irregular but deeply patterned structure. Let us pause for a moment and think about clouds. Have you ever tried to draw a real cloud? It is almost impossible. A cartoon cloud is simple enough, just a fluffy white oval with a few gentle bumps. But a real cloud has that complex, textured, frothy edge, full of little curls and wisps that seem to echo the larger shape of the cloud itself. You cannot draw a convincing cloud with a simple ruler and a compass. Its edges are too complex. But fractal equations can generate images that look uncannily like real clouds, capturing that natural irregularity. Fractals give us a tool, a language, for modeling the beautiful messiness of the real world. And then there is the startling instantaneous beauty of a lightning bolt. A single brilliant fork of lightning splits the sky, and then in a fraction of a second, it splits again and again and again in branching, jagged paths that look eerily similar no matter how far you zoom in. That branching structure is a perfect, fleeting fractal. And that very same basic form shows up in the branching of river networks as they carve their way to the sea, in the vast network of blood vessels that carries life through your body, and even in the silent, searching tips of tree roots deep underground. It is nature's favorite way of building a distribution network, a branching system that allows things to move, electricity, water, blood, nutrients, through a space with incredible efficiency. The tree is a particularly elegant example. When you look at the branching of an oak tree in winter, its dark skeleton against a pale sky, you can see it so clearly. Each large branch splits into smaller branches, and those divide into even smaller twigs. The angles and lengths are not perfectly identical, but the structure echoes itself at every single level. This is how a tree solves the problem of capturing sunlight.
creating a vast surface area for its leaves without wasting precious space or energy. It is evolution, sculpting geometry with a slow, biological chisel. And these patterns do not just appear in the visible structures of living things, they are also fundamental to how those things function. Take a deep, slow breath. As the air enters your lungs, it doesn't just fill two big pink balloons. Inside your chest, your airway branches again and again into smaller and smaller tubes called bronchioles, ending in millions of tiny, delicate air sacs called alveoli. This fractal branching system allows an enormous surface area to be packed into a relatively small and protected space. It is estimated that if you could flatten out the surface of your lungs, it would cover an area roughly the size of a tennis court. All of that tucked neatly and safely inside your chest, a life-giving biological fractal at work with every breath you take. Even the rhythm of your own heart has fractal patterns hidden within it. When your heart is healthy and relaxed, the time between each beat does not stay perfectly mechanically even. It varies, just slightly, in a pattern that is complex, subtle, and self-similar over time. Too much regularity in a heartbeat can be a sign that something is wrong. Too much chaos is not good either. A healthy, resilient heart has a rhythm that is just irregular enough, dancing gracefully between order and disorder, much like the edge of a cloud or a coastline. Now, let us drift for a moment from the organic world into the pure, quiet world of mathematics to look at the most famous fractal of all. It is an image you may have seen before, known as the Mandelbrot set. It looks like a strange, black cardioid shape with a large circle attached to one side and countless smaller circles butting off from its edges. But as you get closer, you see that its boundary is not smooth at all. It's an infinitely complex coastline of swirls, curls, and fine hair-like filaments that stretch out into beautiful, chaotic patterns.
It is named for Benoit Mandelbrot, of course, and it is generated using a very simple equation applied to the numbers on a complex plane, repeated over and over and over again. The incredible, almost magical thing about the Mandelbrot set is that if you zoom in on its fuzzy, intricate edge, you keep finding more and more detail. You do not just find tiny, abstract shapes. You find entire new worlds of complexity. You will find tiny, spiraling seahorse tails, lightning-like branches, and most astonishingly of all, you will find tiny, distorted copies of the entire Mandelbrot set itself, hiding within its own boundary over and over again into infinity. It is like looking into a mirror made of pure mathematics, where each reflection contains another, smaller reflection, each one unique yet hauntingly familiar, just waiting to be explored. And yet all of this infinite, breathtaking complexity comes from one simple rule, patiently repeated. That is the deep, quiet magic of fractals. You begin with a simple instruction, a simple seed of an idea, and you allow it to repeat. With just a few basic rules and a great deal of iteration, something truly astonishing begins to take shape. You do not need a complicated blueprint for the entire structure. You just need to follow the simple rule and let the pattern unfold itself. This, in a profound way, is how nature builds itself. Not with grand, top-down plans, but with simple, local rules carried out billions of times. A tree does not know how to be a tree. Its cells are simply following genetic instructions to divide, to grow a little stem, which then branches. Those branches grow and then branch again, following the same simple rules. The final result is something that looks intentional, majestic, even artistic, but it is all driven by small, humble steps repeated with the unending patience of the natural world.
there is a quiet and powerful lesson in that. In a world where we so often feel the pressure to do big, important things all at once, fractals remind us that staggering complexity can emerge from the simplest of beginnings, that true beauty can arise from gentle repetition, and that something as intricate as a fern or as sprawling as a thunderstorm can be born from just doing the same small thing, thoughtfully, again and again. And just as fractals exist in the physical world, they have also found their way, almost instinctively, into the world of human art and music. Some composers have used fractal algorithms to generate musical patterns that are complex yet coherent. Visual artists have built entire digital landscapes and otherworldly scenes from fractal structures. And the video games and films that transport us to other worlds often rely on fractals to create their lifelike environments, the rugged mountains, the twisting trees, and the realistic coastlines, all born from the simple, repeating logic of fractal geometry. You can also find these patterns woven into ancient cultural artifacts. Traditional African art, Indian textiles, and Islamic architecture sometimes include stunningly complex fractal patterns in their designs. Long before the word fractal was ever invented, humans were already intuitively mimicking these repeating, self-similar patterns in their craft. It seems our brains are naturally, deeply drawn to them, even if we do not always realize why. What is it about these patterns that can feel so deeply soothing? Perhaps it is the way they suggest a sense of endlessness without ever tipping into pure chaos. They give your mind something to follow, a path to trace, without ever overwhelming you with too much information. They are structured, but they are never rigid. They are predictable, but they are never boring. They feel like a walk along a forest trail that winds just enough to keep you curious about what is around the next bend, but not so much that you ever feel lost. Fractals live in that beautiful in-between space, the soft edge of chaos, the gentle shore of order. They are not one thing or the other, they are both at once, forever balancing complexity and calm. And in their branching, spiraling, infinitely detailed forms, they invite you to look deeper, to slow your breathing, to notice the way the world builds itself from the smallest of pieces, and maybe, just maybe, to find a little comfort in the quiet repeating rhythms of the universe. In the early 1960s, a meteorologist at MIT named Edward Lorenz was working on a rather humble problem, trying to predict the weather. In his lab, he had one of the early, room-sized computers of the era, a humming machine of vacuum tubes and wires. On it, he had built a simplified model of the Earth's atmospheric conditions. It was sort of a stripped-down, toy version of a weather system, with a handful of equations representing the dance of temperature, pressure, and wind. One day, he ran a simulation, letting the computer churn out a long forecast of this imaginary weather. He then decided he wanted to repeat part of the simulation to examine a section more closely. To save time, he didn't start from the very beginning. He took the numbers from a midpoint in his first printout and typed them back into the machine. But instead of typing in all 6 of the decimal places the computer had originally used, he rounded them off slightly, typing in only 3. It was a minor difference, something like using the number 0.506 instead of the original 0.506127, an almost imperceptible difference. He set the machine running again and stepped away to get a cup of coffee, expecting the new simulation to unfold nearly identical to the first. But when he returned an hour later, something astonishing had happened. The 2 weather patterns had diverged completely. At first, they were almost the same, but then the tiny rounding off error began to amplify until his new forecast showed a weather system that bore no resemblance to the original. It was as if he had created an entirely different world. This seemingly minor laboratory hiccup led Lorenz to uncover one of the most profound and poetic ideas in modern science, chaos theory. And from his discovery came one of the most famous metaphors in all of mathematics, the butterfly effect. In a lecture he gave some years later, he titled his talk, "Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?" Of course, this is not something that literally happens, but the metaphor captures a deep and humbling truth. In large, complex, dynamic systems, the smallest of changes at the beginning can lead to enormous and unpredictable differences later. Let's slow that idea down for a moment. Chaos, in the scientific sense, does not mean pure randomness or complete disorder. It refers to systems that are perfectly deterministic. That is, they follow strict, unwavering rules, but whose long-term outcomes are impossible to predict because of their extreme sensitivity to initial conditions. Imagine two small, identical balls placed at the very top of a hill to roll down. If you start them from the exact same position, they will follow the exact same path. But what if you start one just a single millimeter to the left of the other? At first, their paths will look almost identical. But if the hill is covered in small bumps, gentle curves, and twisting gullies, that tiny initial difference will be magnified with every bump they encounter. Soon, they will be rolling on entirely different parts of the hill, and by the time they reach the bottom, they may be nowhere near each other.
That is what Edward Lorenz saw in his weather model. He hadn't broken the rules of physics, he had followed them perfectly. But the results were wildly unpredictable, because the system itself was just that sensitive. This profound realization was both thrilling and deeply humbling for the scientific world. It meant that, in theory, even if we had the most powerful computers imaginable and the most perfect equations for the atmosphere, we could likely never predict the long-term weather with perfect accuracy. Not because the universe is random, but because it is simply too complex. We could never possibly measure the exact position and velocity of every single molecule of air, every gust of wind, every tiny butterfly wing. Chaos theory soon found its home in all sorts of natural systems. Weather remains the classic example, but the very same principles apply to the delicate balance of ecosystems, the majestic dance of planetary motion, the rise and fall of animal populations, and even the intricate firing of neurons in the human brain. Anywhere you find a system with feedback loops, where the output of an action feeds back to influence the next action, anywhere you find nonlinearity, where cause and effect are not simply proportional, and anywhere you find lots of interacting parts, chaos is just waiting patiently around the corner, humming a quiet, unpredictable tune. Let us consider a much calmer, closer to home example: a dripping faucet in a quiet kitchen. You might think a leaky tap is just a simple, annoying sound. But researchers who have studied the timing of those drips have found the signature of chaos hidden within them. When the tap is dripping very slowly, the drops fall in a steady, predictable rhythm. Drip, drip, drip. Perfect timekeeping. But if you open the valve just a tiny bit more, the pattern changes. The drips might start falling in pairs. Drip, drip, pause. Drip, drip, pause. A little more, and they might fall in groups of 4. And then as the flow increases just a little bit more, the system dissolves into chaos. The pattern of drips becomes wildly unpredictable, never repeating. Even though the physics of the water, the gravity, and the pressure have not changed, the system has simply moved from a state of simple stability into one of beautiful, dynamic chaos. Now, imagine that same principle playing out on the grand scale of an ecosystem. A tiny, seemingly insignificant change, a slight increase in the average temperature of a lake,
the introduction of a new insect. A small shift in rainfall can ripple outwards, cascading through the intricate web of life and creating entirely new balances, or imbalances. Chaos theory helps to explain why ecosystems can sometimes suddenly collapse or transform, even when the change that triggered it was so small it was barely noticed. A few too many fish are caught from a river. A patch of forest just a little too large is cleared, and suddenly, the dominoes begin to fall in ways no one could have predicted. But chaos is not always a harbinger of doom. Far from it. It is also the engine of creation, the source of complexity. It is how simple rules can give rise to rich, dynamic, and endlessly fascinating patterns. Think of a great flock of birds swirling in the evening sky. There is no leader, no choreographer, and yet the group moves as one, a fluid, living cloud. This is an emergent behavior built on the simple, chaotic interactions of individual birds, each one following its own simple rules. And from that local chaos, a global, graceful order is born. In the world of mathematics, these chaotic systems often produce stunningly beautiful images, known as strange attractors. These are visual representations of the path a system takes over time. It never settles into a single fixed point, nor does it repeat in a simple, endless loop. Instead, it spirals, twists, and folds back on itself, tracing an infinitely detailed pattern that never crosses its own path and never repeats. The most famous of these is the Lorentz attractor, the very pattern discovered by Edward Lorenz from his weather simulations. It is a set of swirly, looping curves that look, remarkably, like the wings of a butterfly, an accidental mathematical poem. This healthy, beautiful chaos is even present in your own body. As we touched on before, your resting heart rate, your quiet breathing patterns, they both show signs of chaos. Not a dangerous random fluttering, but a complex, non-repeating variation that is a sign of your body's health and adaptability. A perfectly regular, metronome-like heartbeat might in fact be a sign of a system that is too rigid, too inflexible. The healthy human body thrives in that gentle edge zone, both stable and responsive, predictable and yet flexible. Let us wander for a moment out into the vast, silent theater of space. Our solar system looks like a model of perfect order, with planets tracing neat elliptical orbits around the sun like marbles on invisible strings. But even here, in this clockwork universe, chaos gently sneaks in. The constant gravitational interactions between the planets create tiny, infinitesimal nudges and pulls on one another. Over millions and billions of years, these tiny nudges can accumulate, leading to unpredictable shifts in their orbits. The motion of asteroids in particular can be wildly chaotic. A small change in velocity or position, caused by a close pass with Jupiter, can be enough to fling an asteroid across the solar system, or send it on a path we can never fully predict. Thankfully for us, space is very, very big, and chaos tends to take its sweet geological time. If all of this sounds a little unsettling, a little too unpredictable, here's the comforting part. Chaos is not the enemy of calm. In fact, they often coexist in the most beautiful of ways. There is a quiet, deep elegance in watching how the world balances between them. You can't predict the exact path of every single falling leaf in a forest, but you can feel the calm of the forest as a whole. You can't know the shape of the next flicker in a campfire, but you can feel its steady warmth. In nature, chaos creates diversity. It prevents stagnation. It encourages adaptation. A perfectly ordered system would be brittle, unable to change. A purely random one would be unworkable, unable to build anything lasting. But chaos systems dance gracefully between the two. Think of a river. It is always flowing, always changing, never the same river twice. Yet it is always a river, always following the unwavering pull of gravity. Or that campfire, its flames flickering, leaping, changing shape every second, yet still contained, warm, and inviting. That is chaos in its softer form, not destruction, but dynamic, living beauty. And while chaos theory has its solid foundation in mathematics and physics, it is also deeply philosophical. It invites a sense of humility. It reminds us that certainty is often an illusion, that our control is limited, and that small, quiet acts truly matter. You never know what subtle, gentle influence your own presence, your own quiet choices might have in a room, in a day, or in a life. This does not mean we should live in fear of consequences we cannot predict. Quite the opposite. It means we can take comfort in the unpredictability. The world is allowed to surprise us. The future is not a fixed written story. There is always room for spontaneity, for change, for the unexpected and wonderful turn of events. At the very heart of chaos theory is a simple but profound truth. Even in systems governed by the strictest of rules, the future can be a beautiful, unfolding mystery. And this is not a flaw in the universe. It is a feature. It is what makes the world interesting, alive, and endlessly full of possibility. The butterfly effect is not just a quirky metaphor. It is a gentle, soothing reminder that even the tiniest actions can echo through time and space. That somewhere, in some great unfolding chain of events, a small gesture of kindness, a passing, hopeful thought, a single, quiet choice, might just be the beginning of something much, much bigger than you could ever imagine. And there is a certain profound peace to be found in that. Now, let us bring our focus back from the vastness of space and the grand sweep of time and land softly, gently in the middle of a quiet forest. Imagine yourself standing there, not rushing through on a hike, not checking your phone for a signal or worrying about where the path might lead, just standing. The air is cool and smells of damp earth and pine. Above you, a high canopy of leaves filters the sunlight into a soft, dappled green glow that dances on the forest floor. Listen. Can you hear the sound of the wind as it moves through the leaves? Not as a single gust, but as 1,000 tiny whispers. Listen to the slow, deep creak of branches as they sway. And as you stand there in that stillness, you might begin to feel, even if you do not consciously realize it, that there is something deeply, profoundly harmonious about the shapes that surround you. Trees do not just grow, they arrange themselves, and in their slow, silent, patient way, they follow the laws of geometry. Let us begin with something so simple, so familiar, that it is incredibly easy to overlook: the way a tree branches. You have seen it countless times, of course. A great solid trunk splits into a few thick, sturdy limbs. Those limbs divide again into smaller branches. Those branches fork into a delicate lace of twigs, and at the end of each twig, a cluster of leaves or needles reaches for the light. It looks natural, organic, perhaps even random. But there is a quiet, steady mathematics humming gently just beneath the surface. Trees do not branch by accident. They follow certain unwritten rules, elegant solutions that have been refined by evolution over millions of years to help them survive, thrive, and grow towards the light. One of those rules involves branching angles. That is, the angle at which a new branch grows out from its parent branch. It turns out that this angle is not a fluke. It is an optimized solution to a difficult problem. If the angle is too small, the branches will grow too close together, crowding each other and blocking their own precious access to the sunlight. If the angle is too wide, the branch might be structurally weak, unable to support the weight of its own leaves or the burden of winter snow. But somewhere in the middle, often around 38 to 45 degrees for many species, there is a perfect sweet spot. A delicate balance between strength and exposure to the sun. This optimal angle allows each new branch to maximize its own light capture while minimizing the shadow it casts upon its siblings. It's a little like being in a crowded theater. You could sit directly behind the person in front of you, but you wouldn't see a thing. You could sit too far to the side, and your view would be skewed. But there is one perfect spot that gives you the best possible view of the stage without getting in anyone else's way. Trees are experts at finding that spot. And that's just one part of the geometry at play. Another crucial concept is something called phyllotaxis. This refers to the arrangement of leaves on a stem or a branch. In many plants and trees, if you look closely, you will see the leaves are not arranged directly opposite each other, but in elegant spirals that wind their way up the stem. And what is the angle of rotation between each leaf in that spiral? Very often, it is our old friend, the golden angle, that same 137.5 degrees we found in the heart of the sunflower. This arrangement allows for the most efficient packing of leaves, ensuring that each one gets a clear and unobstructed shot at the sun. It's a quiet, graceful choreography, all in the pursuit of light. Because sunlight is energy, and energy is everything to a tree. Every single inch of its growth, every cell of its wood, every drop of its sweet sap is powered by light, captured and turned into sugar through the magic of photosynthesis. So it makes perfect sense that trees would evolve to become incredibly efficient masters of harvesting that light. The geometry of their branches and leaves is the beautiful result of millions of years of evolutionary tinkering with the quiet economics of energy. Even the height of a tree is a breathtaking balancing act of physics. Taller trees can outcompete their neighbors for light, but they are also faced with a monumental challenge of transporting water all the way from their deepest roots, hundreds of feet up, to their highest leaves, defying gravity every single inch of the way. Imagine being a single molecule of water being absorbed by a root tip deep in the cool, dark earth beneath a giant coastal redwood. You begin your journey upward, pulled into a vast network of microscopic tubes called xylem. You are pulled not by a pump, but by the power of evaporation from the leaves high above, and by the incredible cohesion between water molecules themselves, a force that allows you to cling to your neighbors, forming an unbroken chain of water stretching from soil to sky. It's an elegant and silent system, but it is not without limits. Gravity, friction, and the sheer physics of it all eventually put a cap on how tall a tree can possibly grow. There is even a theoretical maximum height for any tree on Earth, somewhere around 430 feet, beyond which the delicate, life-giving column of water would simply break under the strain. Now let us look at the tree as a whole. Its overall shape, the strong trunk rising, the great branches spreading, the deep roots anchoring, is not just a consequence of random growth. It is a living, breathing solution to a complex mathematical puzzle. How do you expose the most possible surface area to the light while using the least amount of material to build your structure, all while remaining strong enough to withstand the forces of wind and weather? The answer, once again, lies in the repetitive, self-similar patterns of fractals. The structure of a tree is fractal in its very nature. A large branch, if you were to look at it alone,
resembles a smaller, younger tree. A single twig echoes the branching pattern of the mighty limb it grew from. This fractal pattern is not just beautiful, it is incredibly efficient. It allows the tree to cover the most space, collect the most light, and transport the most nutrients, all with minimal material and energy costs. Fractals appear in trees because they are nature's perfect solution to a specific problem: how to fill a three-dimensional space effectively. The branching pattern creates a vast network where every part is connected, yet everything is gracefully spread out. This is especially vital for the unseen part of the tree, its root system. Roots, just like branches, grow in a fractal way, allowing the tree to explore a vast volume of soil with a relatively small amount of biological material. The root system is an underground mirror of the canopy high above, a twin pattern growing in the opposite direction, silently seeking water and nutrients, just as the branches above are seeking light. And this type of branching, fractal structure is not unique to trees. We find it everywhere in the biological world: the network of blood vessels in your own body, the bronchi in your lungs, even the delicate branching dendrites of the neurons in your brain. All of them follow these same similar fractal rules. The logic is always the same: spread out, reach many places, and do it with the utmost efficiency. In your brain right now, as you listen, your neurons are branching like tiny, intricate trees. Their dendrites reach out like roots and branches, seeking and receiving signals from other neurons. The very shape of these networks affects how you think, how you remember, how you feel. It is, in a very real sense, trees all the way down, living mathematics, shaping biology. There is something deeply, deeply poetic about that. Trees are not just biological organisms, they are physical manifestations of timeless mathematical principles. You can describe their essential shape with algorithms, simulate their growth with computer models, and even recreate their branching patterns in sculpture, architecture, and digital art. And yet, for all this underlying logic, no two trees are ever exactly alike. They all follow the same fundamental rules of growth, but the final results vary with the subtle shifts of wind, the quality of the soil, the competition from their neighbors, and the pure, simple element of chance. It is as if each tree is writing its own unique version of a familiar and ancient poem, using the same calming rhythm, but with different, personal words. This adaptability is part of their quiet genius. A tree can sense where light is most abundant and will redirect its growth accordingly. It will lean, twist, or even reshape itself entirely over the years to find the best possible position for its own survival. And beneath the soil, another layer of complexity pulses quietly. Trees in a forest are often connected by a vast, intricate network of fungi, an underground system sometimes called the wood wide web. Through this network, they can exchange nutrients, share information, and even warn their neighbors of stress or danger. It is a hidden, silent community, adding another layer of wonder to this already intricate geometry. But for a moment, let us step back. Think not just of the tree's function, but of its pure form. The way its branches stretch upward toward the sky, the graceful curve of a bough in winter, the delicate, intricate lace of bare twigs against a pale evening sky. There is a reason that people have drawn, painted, sung about, and studied trees for all of human history. Their structure is captivating. It feels both deeply familiar and wonderfully mysterious at the same time. They are quite literally living equations, quietly solving for light, for water, for strength, and for balance. And yet, for all their mathematical precision, they never seem cold or mechanical. Quite the opposite.
There is a kind of deep, abiding calm in their order, a profound rhythm, a slow, steady breath drawn over centuries. The geometry of trees is not just about how they grow. It is about how they work, how they optimize, how they adapt, and how they endure. How they manage to be so perfectly efficient without ever losing their grace. They are silent, patient mathematicians of the forest, and all we ever have to do to appreciate their work is to slow down, look up, and let their branches do the talking. Now, let your mind drift from the quiet, rooted stillness of the forest. Let us travel in our imagination to a different place, a place of water and sand and endless horizons. Let us walk along the edge of a calm sea just as the tide begins to recede. Imagine you look down and see, half buried in the damp sand, something small, quiet, and perfectly curved, a seashell. You pick it up. It is still cool and damp from the ocean, and it rests comfortably in the palm of your hand. Its surface is smooth, and its colors are soft and sun-faded, creamy whites, soft pinks, gentle browns. You turn it over gently, and you notice its incredible shape. The way it curves inward, curling like a frozen wave or a spiral staircase to a tiny hidden world. It begins tightly at one end and slowly, gracefully widens as it swirls outward. This is not a random curve, and it is not even just a pretty one. That curve is mathematical. That curve is ancient. That curve is a logarithmic spiral. The logarithmic spiral, sometimes called the equiangular spiral, is a very special kind of pattern. It's a curve that keeps turning while at the same time getting progressively farther from its center point. But it does so in such a smooth, steady, and proportional way that it looks almost hypnotic. The key feature is this. With every quarter turn the spiral makes, it grows by the exact same factor, not by the same amount, but by the same ratio. That is the quiet magic of it. The spiral expands, but it does so without ever changing its fundamental shape. It's like nature took a compass to draw a perfect swirl, but the pencil moved farther away from the center at just the right consistent rate each time around. You can see this beautiful spiral hiding in all sorts of shells, but the most iconic and famous example is the nautilus. This beautiful, mysterious marine creature with its great coiled shell and its crown of searching tentacles is something of a living fossil. Its ancestors have been around for hundreds of millions of years, cruising silently through the deep oceans while the dinosaurs still stomped on land. The nautilus builds its shell by adding new, larger chambers as it grows. Each new chamber it adds is larger than the last, but it follows that same gentle logarithmic curve, perfectly maintaining the spiral. The shell doesn't curl tighter and it doesn't flatten out. It holds that perfect curve again and again, as if it's following some deep internal blueprint, a mathematical guide printed right into its very DNA. But the nautilus does not do this just to be stylish. The spiral is profoundly functional. Each new chamber the nautilus builds is part of an ingenious buoyancy system. The older, smaller chambers are sealed off and filled with gas, while the creature lives in the newest, outermost one. By carefully controlling the amount of gas and fluid in these chambers, the nautilus can adjust its buoyancy, allowing it to float up or down through the water like a slow-moving organic submarine. The logarithmic spiral is what allows the nautilus to grow without ever changing its essential shape. This means it can maintain its perfect proportions as it ages. No awkward growth spurts, no redesign required. It is a clever, efficient strategy, and it is one that does not require reinventing the wheel with each birthday. Just add a new chamber, stick with the spiral, and carry on. Other mollusks use this same quiet logic. Many gastropods, like snails and whelks, grow their protective homes in spirals too. Even the ammonites, those extinct ancient relatives of the nautilus, followed the same beautiful formula. Their fossilized spiral shells found in rocks around the world, a silent testament to a pattern that worked for millions of years. But shells are not the only ones in on the spiral secret. Spirals show up in plenty of places where shells are not involved at all. Look up at a satellite image of a hurricane. That vast, swirling mass of cloud is not just dramatic weather. It is also a gigantic spiral, shaped by the rotation of the Earth, the pressure gradients in the atmosphere, and the rising of warm, moist air. And then there are the spiral galaxies. Our own Milky Way, along with billions of others, curls its great arms through the blackness of space in massive, majestic spirals. The stars and gas and dust are drawn together into these graceful, sweeping curves that stretch across hundreds of thousands of light years. And if that is not impressive enough, this same spiral pattern also shows up deep inside your own body. Tucked safely within your inner ear lies the cochlea, a tiny, spiral-shaped, hollow bone that helps you to hear. This minuscule organ is curled into a spiral to conserve space while maximizing its surface area. Inside, it is filled with fluid and lined with thousands of tiny hair cells that vibrate in response to different frequencies of sound. The spiral shape allows your ear to decode the pitch of sounds with remarkable precision. In a way, your ear is a very quiet mathematician, unwinding the sound of the world into its component parts. From the spin of a galaxy to the way you hear these words, it all seems to come back to the same thing: the spiral as an efficient, elegant, natural solution. And as is so often the case in nature, what is practical also becomes beautiful. Spirals also turn up in so many other living forms once you begin to look for them. The proud curling horns of a ram, the delicate sticky beginnings of a spider's web, the searching, hopeful tendrils of a climbing plant, spiraling as they reach for support. Even DNA itself, the very blueprint of life, while a double helix rather than a flat spiral, still reflects this fundamental idea of twisting, repeating symmetry. The spiral form, in all its countless variations, seems to whisper something fundamental about the way energy, growth, and structure come together in our universe. And there is something oddly, deeply comforting in that. Despite all the breathtaking complexity in nature, despite the sheer, endless variety of forms and colors and functions, certain essential shapes come back again and again. The spiral is one of them. Whether you are looking at a sunflower in your garden, a seashell on the beach, or a galaxy millions of light years away, the shape feels familiar, recognizable, and deeply reassuring. It is as if the universe, in its quiet moments, keeps doodling the same beautiful curve in all of its different notebooks. And it's worth remembering that nature is not obsessed with mathematical purity. It's not trying to perfectly match a diagram in a textbook. Many natural spirals are only approximations of the famous golden spiral. Some are a little steeper, some a little shallower. Nature rewards functionality above all else. If a shell grows slightly off course, but still provides a safe and efficient home, that is perfectly fine. The spiral, like so many patterns in nature, is flexible. It allows room for variation, for adaptation, for life itself. And so when you hold a shell in your hand, you are not just holding an object, you are holding a timeline. The entire life of a small creature, traced in calcium carbonate, winding outward in a precise and elegant arc. You are holding a quiet echo of the same curves that shape the storms, the galaxies, and the very mechanism of hearing inside your own head. A soft, gentle spiral written over and over again in nature's patient notebook. Now let your mind drift from the curve of the spiral and turn instead to another of nature's perfect forms. Let us go back to the image of a swirling cloud, but this time, let us imagine it's a cold winter cloud, high in the atmosphere. And inside that cloud, something almost magical is beginning to happen. A tiny speck of dust, or perhaps a grain of pollen, floats in the supercooled air. A molecule of water vapor finds it and freezes onto it, forming a tiny, six-sided crystal of ice. This is the humble beginning of a snowflake. As this tiny seed of a snowflake begins its long, slow, tumbling journey down to the earth, it is shaped by the air around it. The temperature and the humidity of the clouds it passes through are constantly changing, and these subtle, ever-shifting environmental conditions influence how the crystal grows. First, simple facets may form. Then, as conditions change, elegant, branching arms begin to grow from its six corners. The six-fold symmetry comes from the very molecular structure of water itself. When water molecules freeze, they naturally arrange themselves into a hexagonal lattice, and that perfect, microscopic symmetry echoes outward as the entire flake grows.
You have likely heard the famous saying that no two snowflakes are exactly alike, and this is almost certainly true. Each flake follows its own unique path through the sky, experiencing its own unique history of temperature and moisture, and so each one becomes a unique frozen record of its journey. And yet, they all follow the same fundamental six-sided rule. The breathtaking symmetry arises not from a grand design, but from consistency. Because each of the six arms of a single snowflake grows outward through the exact same atmospheric conditions at the exact same time, they tend to mirror each other's growth with astonishing precision. It is a kind of spontaneous, emergent order. You do not need a designer. You do not need a blueprint. You just need water, cold air, and the patient, gentle hand of physics. Each tiny flake that falls is a six-sided work of art. Intricate, delicate, symmetrical, and beautifully fleeting. It is nature's frozen geometry, drifting silently down from the sky. Now, let us shift our gaze from the crystalline symmetry of frozen water to the liquid symmetry of soapy water. Picture a soap bubble, a shimmering, floating, perfect sphere catching the light and reflecting the world in its curved surface. It lasts only for a few moments before it pops and vanishes. Unlike snowflakes, which form through the slow process of crystal growth, bubbles are shaped by a force called surface tension. It is a force that pulls the molecules at the surface of a liquid together, drawing them into the tightest possible shape. And what is that most efficient, most perfect shape? It is always a sphere. This is not a coincidence. A sphere is the one shape in the universe that can enclose the most volume with the very least amount of surface area. Nature adores efficiency. And so when a thin film of soap and water stretches around a puff of air, surface tension pulls it into the shape that requires the minimum amount of energy to maintain. And the sphere wins every single time. But bubbles do not stop at being pretty. They also reveal how geometry can emerge from simple physical forces. If you gently press two bubbles together, they will meet and flatten slightly, forming a perfectly straight wall between them. If you bring three bubbles together, their shared walls will always meet at a precise angle of 120 degrees. And when many bubbles are packed together in a froth, they naturally form hexagonal patterns, like a beautiful, chaotic mosaic. It is all very polite and very mathematical, as if the bubbles have an unspoken agreement to share their space as fairly and efficiently as possible. You can find this very same hexagonal pattern in the structure of a honeycomb.
where bees build their wax cells in perfect hexagons because it is the shape that uses the least amount of wax to hold the most amount of honey. Once again, it's geometry doing its quiet, efficient work. And this love for symmetry shows up everywhere in nature. Flowers often display beautiful radial symmetry, their petals arranged in circles of 3 or 5 or 6. A starfish has 5 arms arranged symmetrically around a central point. Even the simplest of creatures, like a floating jellyfish, display this same rotational symmetry. For many organisms, symmetry offers practical evolutionary advantages. It helps with balance, with movement, and sometimes even with camouflage. A symmetrical body plan allows an animal to move efficiently and stay oriented in its environment. In us humans, symmetry is especially intriguing. Our bodies are built with what is called bilateral symmetry. 2 arms, 2 legs, 2 eyes, 1 nose, right in the center. We are essentially built as 2 mirror images, joined down the middle. Of course, we are not perfectly symmetrical. One of your feet is likely a tiny bit bigger than the other. You almost certainly have a dominant hand and a stronger eye. But the general layout holds true. And one of the biggest reasons for this is that it simplifies our biological development. Our DNA does not need to write a separate, complex set of instructions for the right side and the left side. It can simply use the same blueprint and flip it. But our relationship with symmetry is not just physical, it's deeply psychological. Countless studies have shown that humans, across all cultures, tend to find symmetrical faces more attractive. Not because we are shallow, but because our brains are exquisitely wired to process symmetry with great speed and ease. Symmetrical patterns are easier to recognize, easier to remember, and in the deep evolutionary part of our brain, they often serve as a quiet visual signal of good health and stable development. We see symmetry as a sign of balance, a kind of visual trustworthiness. This might explain why symmetry appears so often in our own art, design, and architecture. From the balanced columns of ancient temples to the clean lines of modern logos, symmetrical patterns create a sense of harmony, of peace, of rightness. They are pleasing to the eye and deeply soothing to the brain. There is a reason that mandalas, those intricate circular designs used in many cultures as a tool for meditation, are always symmetrical. Their repetitive, mirrored patterns provide an anchor for the wandering mind. They invite focus, calm, and a deep sense of contemplation. But nature, in its infinite wisdom, does not limit itself to one kind of symmetry. And it also understands the profound importance of breaking symmetry. Think of a fiddler crab with one great oversized claw and one small, delicate one. Or a tree on a wind-swept cliff, its branches growing almost entirely on one side, permanently leaning away from the wind. These asymmetries are not flaws. They are adaptations. They are solutions. In the great unwritten book of biology, function always takes priority for perfect form. If breaking symmetry offers a creature an advantage in survival or reproduction, then evolution is more than happy to do so. Even within your own brain, symmetry and asymmetry live together in a beautiful partnership. The 2 hemispheres of your brain are physically, broadly symmetrical, near mirror images of each other, but they are functionally distinct. For most people, the intricate machinery of language resides primarily in the left hemisphere, while the processing of spatial relationships and emotional tones lean toward the right. The symmetry of the brain provides the underlying structure, while its asymmetry provides for elegant specialization. It is a perfect balance of form and function.
And there is something so deeply human about our fascination with these patterns. We find symmetry in snowflakes and soap bubbles, in the faces of those we love and the slow unfolding of petals. We seek it out, and we replicate it in everything from our grandest architecture to the simple pattern of a knitted scarf. And yet, we also recognize the unique beauty of asymmetry, a jazz solo that veers off in an unexpected direction, a painting with an off-center subject that draws your eye, a story with a surprising and delightful twist. Too much perfect symmetry can begin to feel rigid, static, even lifeless. Too little, and things dissolve into incomprehensible chaos. The sweet spot, the place where life and beauty truly thrive, lies somewhere in between. Just enough order to feel stable, just enough variation to stay interesting. And this balance is perhaps why natural symmetry feels so deeply satisfying. It never seems to try too hard. A snowflake does not strive to be perfect, it just is, quietly following the laws of physics, forming silently as it falls. A soap bubble does not plot and plan its spherical shape, it is simply the inevitable, beautiful result of tension and air. The patterns are not forced, they emerge. Symmetry speaks to something deep within us. Perhaps it is the part that craves order in a sometimes disordered world, the part that seeks meaning in patterns. Or maybe it is simply that in a universe full of noise, symmetry offers a quiet kind of music, a harmony we can see. And in those soft, silent moments, a single snowflake caught on your glove, a shimmering bubble drifting in the sunlight, you can glimpse the gentle geometry at the very heart of everything, a stillness within the complexity, a simplicity within the swirl. You do not need to understand the math to feel it. It is already there, woven into the fabric of the world around you, balanced, mirrored, and waiting quietly to be noticed. Now, let us zoom out. Let us pull our focus away from the tiny, perfect symmetry of a single snowflake and rise high above the earth until we can see the grand, sweeping patterns of the land itself. Imagine you are staring down at a map and you begin to trace your finger along the outline of a country. Perhaps you follow the winding, intricate edge of a coastline or the jagged, saw-toothed lines of a great mountain range. You might have the curious sensation that the closer you look, the more there is to see. It's like chasing the edge of a puzzle piece that keeps adding new curves, new corners, new complexities every time you squint a little harder. That feeling is not just in your head. It turns out there is real, profound mathematics behind it. Welcome to the world where geography meets geometry, and where the very terrain of our planet becomes a tangled, beautiful web of hidden patterns. Let's begin with that deceptively simple-sounding task, measuring the coastline of Britain. We touched on this earlier, but let's revisit it. From the shoreline, you would think this would be straightforward, but here's where things become wonderfully tricky. If you were to measure it on a large map with a very long ruler, you would get one answer. But if you were to actually walk the coastline with a 1-meter stick, your measurement would be far, far longer. As you followed the curve of every bay, the edge of every inlet, the boundary of every single rock. This famous puzzle, known as the coastline paradox, challenges our very idea of measuring something that appears so concrete. A coastline, unlike a straight line, does not have one single definite length.
Its length depends entirely on the scale at which you choose to measure it. The more detail you are willing to capture, the more complicated and longer the line becomes. The reason this happens is because coastlines are fractal. Their rugged, beautiful patterns repeat at different scales. If you look at a large satellite image of a coast, you will see great bays and peninsulas. Zoom in, and you will find smaller coves and rocky outcroppings. Zoom in further, and you will see that even the individual rocks have jagged edges, worn by the endless work of the waves into miniature cliffs and tiny folds. The structure continues from kilometers down to meters, and even down to the grains of sand. There is no smooth, simple line to follow. There is just more and more complexity the closer you look. A coastline is a perfect example of a natural fractal shaped over eons by countless forces: the rhythmic push and pull of waves and tides, the slow, patient work of erosion, the great deep movements of tectonic plates. Its shape is a reflection of that long and complex history, a mathematical fingerprint etched into the geography of the Earth. Now, let us shift our gaze inland, away from the edge of the sea and toward the veins of the land, the rivers. From high above, rivers look like a network of branching silvery threads. A main channel meanders through a wide valley, and it is fed by smaller tributaries, which are themselves fed by even smaller streams and creeks. The structure is unmistakably fractal. Each level of the vast network resembles the next, with smaller and smaller forks feeding into one another, like the branches of a great horizontal tree laid out upon the land. This is not just a coincidence. It is the inevitable result of physics, of gravity and erosion working together patiently over immense spans of time. As water flows downhill, it seeks the path of least resistance, carving channels that deepen and widen over the centuries. The fractal branching pattern emerges naturally as the entire system works to move water from the land to the sea as efficiently as possible. In fact, river networks are so consistent that they follow unwritten laws, not laws passed by governments, but deep statistical relationships known as scaling laws. One of them, called Hack's Law, describes the elegant mathematical relationship between the length of a river and the size of the area that it drains. The complexity of a river system, while it looks chaotic, is in fact an expression of a hidden mathematical order.
And this same quiet order emerges in the way that rivers meander. If you have ever flown over a flat landscape and seen a river that winds back and forth in lazy looping curves, you have witnessed another kind of natural pattern. Rivers do not always flow in straight lines. Instead, they gently erode their outer banks while depositing sediment on their inner banks, causing their bends to grow and shift and snake across the floodplain over time, sometimes even looping back to cut themselves off, forming a beautiful crescent-shaped oxbow lake. These meanders follow predictable rules, too. There is even a consistent mathematical relationship between the length of a river's curves and the width of its channel. It is almost eerie in its precision, as if the river itself knows exactly how much it should twist and turn. The same forces that shape rivers also sculpt our mountains. And while mountains may at first appear to be the very definition of chaos, a great random jumble of peaks and cliffs and ridges, they too follow these same quiet patterns. If you look closely at the silhouette of a mountain range against the sky, it shares that same fractal quality, jagged and intricate at every scale. Great ridges split into smaller ridges, which in turn split into sharp arêtes, and deep gullies, which split again into the smaller features of a single cliff face.
The process that creates these majestic forms, the immense slow-motion collision of tectonic plates pushing the land upward, combined with the relentless, patient sculpting power of wind, water, and ice, plays out over geological timescales that are almost impossible to comprehend. But the resulting geometry is quietly, beautifully consistent. And once again, this is a kind of complexity that arises from simplicity. Scientists can now create stunningly realistic computer models of landscapes using relatively simple, repeated rules. They can simulate particles of sediment falling and sticking, or the slow process of water eroding a digital surface. And by repeating these simple actions millions of times, they can generate virtual landscapes that look just like the real thing. It is a profound and common theme in nature. The most intricate patterns, the endless branching of rivers, the craggy face of a cliff, the infinitely complex outline of a coastline do not require an elaborate master plan. They emerge naturally and patiently from the simplest of rules interacting with the world over time. Add water, add gravity, add an immensity of time, and the hidden math reveals itself. There is a kind of deep, quiet satisfaction in knowing that the messy, rugged outline of a cliff face or the erratic looping bend in a river is not truly random. It is the logical and beautiful result of processes that are ordered, repeatable, and profound. The gentle curves of a stream, the deep folds of a valley, the harsh, proud spines of a mountain, all of them have been shaped by water flowing ever downward, by rock resisting and then eventually yielding, and by time pushing ever steadily forward. The earth writes its story in a very slow handwriting, but the equations are there, hidden in the land, if you only know how to read them. And so the next time you find yourself gazing out at a landscape, whether it is a windswept coast, a winding stream, or a distant silent mountain, know that hidden in its forms is a quiet mathematics, a story told in curves and angles and repeating fractal lines. A story written not with ink, but with gravity and water and stone. And once you begin to see it, you will find it everywhere. In every ripple, every ridge, every line drawn by the earth's patient, steady hand. Now, let us lift our gaze from the slow, patient patterns of the earth and turn our eyes to the sky, just as the sun is beginning to set. Imagine you have seen it before, perhaps on a quiet evening walk, a great flock of birds, maybe hundreds, even thousands of them, swooping and swirling together in the air. They form shapes that shift and ripple like a sheet of dark silk caught in the wind. There is no leader out in front barking instructions, there are no flashing lights to guide their path, and yet somehow they move as one. They twist, turn, dive, and rise, all without ever colliding. It is mesmerizing, almost hypnotic, and it is strangely, deeply mathematical. This type of coordinated, seemingly intelligent group behavior, whether we see it in birds, in fish, in insects, or even at times in crowds of people, is known as emergent behavior. It is what happens when a multitude of individuals all follow a few simple rules, and from those simple rules, a complex and beautiful group dynamic emerges. No one bird is in charge, no single fish dictates the direction of the school. Each member of the group simply pays attention to a few of its closest neighbors, and a magnificent coordinated pattern unfolds naturally from those local interactions. Take starlings, for instance. When they gather in those breathtaking, swirling clouds in the sky, a phenomenon known as a murmuration, they are each responding only to the position and the movement of about 6 or 7 of the birds flying nearest to them. That's all. They don't have to track the entire flock, which would be an impossible task. by simply aligning themselves with their immediate neighbors, keeping a small but safe amount of space, and adjusting their speed to match. They collectively create an intricate and spontaneous dance in the sky. Fish do something remarkably similar. Great schools of fish can move in tight, shimmering formations, shifting their direction almost instantly when a predator approaches, or turning in perfect fluid arcs as if they have been choreographed. Each fish is reacting not to the group as a whole, but only to the subtle movements of the fish directly beside it.
If one fish turns, its neighbor responds in a fraction of a second. The neighbor to that fish then responds, and the change cascades outward through the entire school like a ripple spreading across the surface of a still pond. It is breathtakingly fast, incredibly efficient, and a profoundly successful survival strategy. This is not telepathy. It is not even conscious, deliberative thought. It is simply a set of deep, instinctual rules, honed by millions of years of evolution. Simple, local rules. Keep close, but not too close. Move in roughly the same direction as your neighbors. Adjust your speed to match. And suddenly, without anyone giving orders, without any master plan, the group becomes a kind of superorganism, a living, breathing system flowing through the water or the air as if it had a single, collective mind of its own. You might wonder how these animals can possibly process all of this information so quickly. But nature, as it always does, has streamlined the process. Birds and fish are not performing complex calculations of trajectories like tiny flying or swimming computers. Instead, their nervous systems are exquisitely wired for these quick, instinctual responses. Visual cues, subtle shifts in the pressure of the water or the air, and the immediate behavior of their neighbors guide them in real time. It is less about thinking and more about reacting. Computer scientists have been fascinated by this kind of behavior for decades, and they have even used it to design powerful algorithms. There is something called the Boyd's model, which was developed by a researcher named Craig Reynolds in the 1980s. It simulates flocking behavior using only 3 wonderfully simple rules for each virtual bird or Boyd. The first rule is separation. Steer to avoid crowding your local flock mates. The second is alignment. Steer towards the average heading of your local flock mates. And the third is cohesion. Steer to move toward the average position of your local flock mates. When these 3 simple rules are applied to thousands of virtual agents on a screen, they produce a behavior that looks uncannily, astonishingly like a real bird flock or a real school of fish. There is no master plan, just simple, local decisions leading to a complex and beautiful global pattern. Now, let us zoom in a bit, from the wide open sky down closer to the ground, and you will find another, more intimate example of this beautiful organized chaos. Let us consider the world of ants. An ant colony can seem, at first glance, like a frantic, directionless buzz of activity. And yet, within that flurry of movement, there is a profound and efficient order. If you watch a trail of ants for any length of time, you will see a method to their movement, a shared purpose. When ants explore for food, they lay down invisible trails of chemicals called pheromones. If an ant is just wandering, the trail is weak, but if it finds a source of food, it will head back to the nest, laying down a much stronger pheromone trail as it goes. Other ants, sensing this trail, will follow it to the food source, and as they too return to the nest, they reinforce that same trail with their own pheromones. Over time, the most efficient and direct path to the food becomes the most heavily used, simply because it is the most heavily reinforced. It is a wonderfully simple, decentralized decision-making system, driven by feedback, chemistry, and the collective effort of the colony.
What is so fascinating is that this emergent process can solve remarkably complex problems. In fact, engineers and computer scientists have borrowed this very idea from the ants to develop powerful optimization algorithms. These so-called ant colony optimization models are now used to figure out the best and most efficient routes for delivery trucks in a busy city or the most effective layout for a complex telecommunications network. Tiny insects, just following invisible scent trails, have helped to inspire the tools that optimize our own modern logistics. And it is not just ants. Bees communicate the location of nectar-rich flowers to their hive mates using an intricate waggle dance, a literal wiggly dance where the angle of the dance relative to the vertical line of the honeycomb tells other bees the direction of the food source in relation to the sun, and the duration of the dance tells them the distance. It's a beautiful abstract language of geometry and movement. Termites, with no blueprint or architect, build towering, complex mounds with intricate internal structures and passive ventilation systems that keep the colony at a constant temperature and humidity. And in some parts of the world, on warm summer nights, thousands of fireflies will flash their lights in perfect rhythmic unison, a living constellation blinking in the darkness, all coordinated by simple local cues. What is so compelling about these systems is their incredible resilience. Because there is no central controller, there is no single point of failure. If a few birds fly off from the flock, the rest of the murmuration continues its dance. If a few hundred ants get lost, the colony still functions perfectly. The system adapts, heals, and carries on in real time. This incredible robustness is something that engineers strive to replicate in our own technology, especially in fields like robotics and artificial intelligence. If you have ever seen a video of a drone swarm with hundreds of small flying robots moving together like a synchronized flock of mechanical birds, you have seen this very principle in action. Each drone follows its own simple rules using sensors and algorithms directly inspired by the behavior of fish and birds. And the result is a coordinated, graceful ballet of machines. It is elegant, it is efficient, and it is a technology borrowed directly from the ancient wisdom of the animal kingdom. What makes all of this even more remarkable is how deeply calming it can be to simply observe. Watching a murmuration of starlings, a shimmering school of fish gliding through the water, or even a slow, steady stream of ants moving along a path has a strangely meditative quality. It feels both chaotic and organized at the same time, full of constant motion, but never rushed. There's a rhythm to it, a natural flow that is hard to describe, but so easy to feel. Part of the appeal, perhaps, is that these systems reflect something we're always looking for: connection without hierarchy, movement without command, and order without control. There is something deeply comforting about seeing hundreds of individuals moving as one, responding to each other, adapting together, and creating a beauty that is far greater than the sum of its parts, all without ever needing to explain how. Now, this idea of a collective, unconscious mathematics leads us to an even more intriguing question. You might not picture a bumblebee holding a tiny calculator or a sunflower solving complex equations, but nature has a very sneaky, very elegant way of doing math without ever writing anything down. Animals and plants do not perform mathematics in the way that we humans do, of course. There are no blackboards in a bird's nest and no spreadsheets in the soil beneath the tree, but that doesn't mean that they're not using sophisticated numerical and geometric strategies every single day. In fact, a surprising number of species show clear evidence of what scientists call number sense, a natural, innate ability to recognize patterns, to optimize their behavior, and to solve spatial puzzles that would make even a seasoned mathematician raise an eyebrow in appreciation.
Let us return for a moment to one of the most mathematically gifted members of the insect world, the honeybee. Bees do not just fly around aimlessly. Their lives are structured, efficient, and astonishingly geometric. And nowhere is that more beautifully apparent than in the perfect architecture of the honeycomb. Each and every cell in a honeycomb is a perfect hexagon, 6 sides of equal length packed together in a flawless repeating pattern that is both strong and beautiful. Hexagons are not the easiest shape for a tiny insect to build, so why do they use them? The answer, as the ancient Greeks first suspected, is pure efficiency. Of all the shapes that can be used to tile a flat surface without leaving any gaps, shapes like triangles, squares, and hexagons, the hexagon is the one that uses the very least amount of wax to hold the most amount of honey. It is the perfect solution to an optimization problem: how to build the strongest, most storage-friendly structure with the absolute minimum of materials and energy. It is advanced mathematics baked right into their biology. But their genius does not stop there. What is even more impressive is that individual bees can understand relative quantities. Studies have shown that bees can be trained to distinguish between different numbers of shapes. For example, they can learn to consistently choose a flower that has 3 blue dots on it instead of one that has 4 in order to earn a sugary reward. They do not count in the way that we do, 1, 2, 3, but they can estimate, they can compare, and they can even understand abstract concepts like more than or less than. For a creature with a brain that is smaller than a single sesame seed, that is nothing short of extraordinary. In one remarkable experiment, bees were trained to associate a certain number of objects with a sweet reward. They quickly learned to recognize these quantities and could even apply simple abstract rules like choose the group that has fewer items. They were, in a sense, performing a basic kind of addition and subtraction. For a creature with a brain no bigger than a pinhead, this is a truly mind-bending accomplishment. Now, let us take to the skies and consider the world of birds. Migratory birds, like the tiny Arctic tern or the incredible bar-tailed godwit, perform some of the most astonishing feats of navigation in the animal kingdom. They travel thousands upon thousands of kilometers across entire oceans and continents, often returning to the very same nesting grounds year after year with pinpoint accuracy. How do they possibly do it? They are not following road signs or checking a GPS. Instead, they are masters of celestial geometry. They carry within them an internal clock and an internal compass, guided by the sun, the stars, and the invisible lines of the Earth's magnetic field. During the day, birds can detect the angle of the sun relative to the horizon, and using their internal 24-hour clock, they can use this information to determine their direction. At night, many use the stars as a navigational map. In a series of beautiful experiments, young birds like the indigo bunting were raised inside a planetarium. They had never seen the real night sky. The researchers found that these young birds learned to orient themselves by observing the rotation of the projected stars. They did not just memorize star patterns, they learned to identify the one point in the sky that did not move, the North Star. And they used this fixed point as the anchor for their entire celestial compass. And as if that were not enough, birds also possess a mysterious sense known as magnetoreception. They are believed to be able to actually see the Earth's magnetic field, perhaps as a faint pattern of light and shadow overlaid on the world, giving them an invisible map to follow even on cloudy days or moonless nights.
What is truly extraordinary is how they integrate all of these different sources of information, the celestial, the magnetic, the topographic, recalibrating their route in real time as they travel. They are, in essence, solving a complex, multivariable navigation problem with their brains, a feat of instinctual, living trigonometry. And birds also display remarkable numerical abilities in their daily lives. Crows, ravens, and parrots, in particular, have shown the ability to count small numbers of objects, to solve puzzles that involve understanding sequences, and even to anticipate future outcomes. In a modern recreation of one of Aesop's fables, crows were presented with a tube of water that was too low for them to reach a floating treat. They quickly figured out that by dropping stones into the tube, they could raise the water level and bring the treat within reach. They even learned to choose larger stones over smaller ones, as if they had an intuitive understanding of volume and displacement. Some researchers even believe that crows and their relatives may understand the concept of zero, an abstract idea that took human civilization a remarkably long time to formally grasp. And even the tiny chickadee, that small, round songbird you might see flitting through snowy branches, organizes its world with a kind of spatial mathematics. Chickadees are famous for caching seeds in hundreds, sometimes thousands of different locations throughout the forest, and then remembering where they put them, sometimes for months. This incredible memory is deeply tied to spatial reasoning. It requires them to create a complex mental map of their environment, a map that mirrors the logic of geometry. It is practical, survival-driven mathematics. Now, let us float back down from the sky, past the branches of the trees, and turn our attention to something even more unexpected. Let us think about plants.
At first glance, plants seem like the very last place you would expect to find number sense. They do not have brains, they do not move quickly, and they certainly do not take math exams. But plants are brilliant problem solvers in their own slow, quiet, and patient way. Consider a plant's root system, that hidden underground world. A plant's roots grow constantly in their search for water and nutrients. And this growth is not random, it is optimized. Root systems follow those beautiful, branching, fractal patterns we spoke of earlier. They split and split again, covering the maximum amount of ground in a way that allows for the most efficient absorption, all while minimizing the energy it costs the plant to grow. Each individual root tip can respond to its local conditions, to gradients of moisture, to the density of the soil, to chemical signals from neighboring plants, and it can adjust its direction of growth accordingly. The overall result is a structure that appears to have been intelligently planned, even though no single part of the plant is actually doing the planning. There is a particularly elegant example of this in climbing plants. Some vines spiral their way upward in search of support, tracing helical paths that often follow the sun's movement across the sky. This behavior, known as circumnutation, involves a constant, slow-motion adjustment of the plant's growth direction, all to maximize its exposure to the light. It is pure geometry in motion. Slow motion, to be sure, but no less precise. And let us not forget our friend the sunflower, which shows its geometric precision so openly. As it grows, its seeds arrange themselves in those perfect, intersecting spiral patterns that follow the numbers of the Fibonacci sequence. It is not that the sunflower is consciously calculating these numbers. It is that the simple genetic instructions that guide its growth naturally and inevitably produce that stunningly perfect arrangement. It is emergent geometry, encoded in the very heart of its biology. And then, there is the strange and wonderful slime mold. Technically not an animal, not a fungus, and not a plant,
This bizarre amoeba-like organism has demonstrated problem-solving skills that seem almost intelligent. In one famous experiment, researchers in Japan placed tiny sources of food on a petri dish, arranging them in the same pattern as the major cities surrounding Tokyo. They then placed a slime mold in the center. Over the course of a day, the slime mold grew outward, creating a network of nutrient-carrying tubes to connect all the food sources. And the final network it created looked remarkably, astonishingly similar to the actual layout of the efficient Tokyo subway system. No central brain, no planning committee, just simple local rules producing a brilliant global solution. All of this raises an intriguing and deeply peaceful question. Where does math really begin? Is it only something that we humans do when we count on our fingers or scribble equations on a piece of paper? Or is it something more universal, something woven into the very fabric of how organisms navigate, survive, and grow? It seems increasingly clear that nature does math in its own quiet, beautiful way, not through symbols or formulas, but through shapes and patterns and behaviors that align perfectly with the deepest principles of mathematics. Hexagons in hives, spirals in seeds, networks in roots, optimization, estimation, measurement, orientation. These are not just human inventions. They are strategies that life itself has evolved over millions and millions of years. And the numbers are always there, humming quietly in the background, guiding the bees as they build, the birds as they migrate, and the roots as they dig. Nature may not be doing math in the way that we understand it, but it is using the very same principles to solve the very same kinds of problems. How to move, how to find, how to build, how to grow. And the math, like everything else in nature, unfolds with a quiet, unhurried precision. The world, as we have seen, is full of patterns in space, but it is also alive with patterns in time. The world is full of rhythms, not just the rhythm of music or the steady ticking of a clock on the wall or the gentle tapping of your fingers on a table, but real, deep, biological rhythms that govern how living things grow and move and rest and wake. You may not feel it consciously while sitting under the artificial glow of electric lights or scrolling through your phone long after midnight, but your body is quietly, faithfully ticking along to a natural, ancient rhythm, a schedule that is millions and millions of years in the making. And it is not just you. From the way a tree drops its leaves in the autumn to the precise night that a sea turtle chooses to lay her eggs upon the sand, all of nature runs on clocks. Not the mechanical kind, but silent, living biological ones. Let us begin with the most familiar and fundamental of these rhythms, the circadian cycle. The name comes from the Latin circa diem, meaning about a day, and it is just that. Nearly every single living thing on this planet, from the smallest bacterium to the largest blue whale, has a circadian rhythm. It is a roughly 24-hour cycle that helps to regulate when to eat, when to sleep, when to move, and when to metabolize. This internal clock is not just a helpful suggestion. It is built into the very fabric of your cells. The master conductor of this grand biological orchestra is located deep in your brain, in a tiny, cross-shaped cluster of neurons called the suprachiasmatic nucleus, or SCN for short. This master clock keeps time using the gently oscillating levels of certain hormones and the rhythmic activity of what are known as clock genes. But these internal rhythms are not isolated. They are tied directly to the great rhythm of the planet, the cycle of light and darkness. When the soft light of morning first enters your eyes, it sends a signal directly to your SCN, which then resets the clock for the day ahead. That is why getting natural sunlight in the morning can feel so invigorating, helping you to wake up and feel alert. And it is why staring at the bright blue-toned light of a screen late at night can confuse your internal clock, delaying the natural onset of sleep. In response to these light cues, your body orchestrates a gentle daily chemical symphony. Melatonin, the hormone that helps you to feel sleepy, begins to rise in the evening as the darkness falls, and its levels drop away in the morning. Cortisol, which helps with alertness and energy, does the very opposite, peaking shortly after you wake. These gentle hormonal waves are what guide your energy levels, your mood, and even your digestion throughout the day.
And this is not just a human feature. Fruit flies, mice, fish, plants, even single-celled organisms show these daily cycles. Flowers open their delicate petals in the morning and close them again at dusk. Fungi release their spores at specific and predictable times of day. And on the great coral reefs of the world, entire colonies will spawn in breathtaking, coordinated bursts, all synchronized by the light of the moon. This biological clock is one of the most ancient and universal features of life on Earth. And it makes perfect sense. Our planet spins, creating a reliable cycle of light and darkness. Organisms that learned to align their biology with this cycle had a profound advantage. Those that could anticipate the coming of day and night could prepare, conserve energy, and stay safer. Over millions of years, this led to the evolution of internal rhythms that match the Earth's rotation almost perfectly. It is a kind of mathematics made of molecules and neurons, ticking away faithfully without a watch in sight. Now, let us zoom out a bit. Beyond the daily rhythm lies a grander, slower, and even more majestic pattern: the seasons. Winter, spring, summer, and fall. An elegant four-part harmony created by the Earth's orbit around the sun. But it is not just the orbit that creates our seasons. It is the tilt. The Earth leans on its axis at an angle of about 23.5 degrees. And as our planet makes its long 365.25-day journey around the sun, different parts of the planet receive varying amounts of direct sunlight. When the northern hemisphere is tilted toward the sun, its light falls more directly upon us, and we are warmed by summer. When it is tilted away, the sunlight strikes us at a shallower angle, and we are cooled by winter. It is a beautiful, silent, geometric dance written in the grand language of orbital mechanics. This slow, seasonal rhythm is the background music to all of life's choreography. Plants bloom, animals breed, birds migrate, and bears hibernate, all in perfect time with the Earth's orbit. Deciduous trees drop their leaves as the daylight wanes, preparing for a long, quiet dormancy. Even the tiny microbes in the soil respond to the deep, slow cycles of temperature and moisture. And then there is the moon, a subtler drummer in nature's great orchestra. The moon does not just light up the night sky. It tugs ever so gently on the Earth with its gravity, pulling at our vast oceans to create the tides. These tides rise and fall with a rhythm that is regular, predictable, and deeply mathematical. This lunar rhythm, which takes about 29.5 days to cycle from one full moon to the next, affects more than just the water. Many animals time their most important behaviors to the moon's cycle. Sea turtles will come ashore to lay their eggs during certain phases of the moon, often around the full moon, when the high tides can carry them farther up the beach. As we mentioned, the great coral reefs synchronize their mass spawning events with the lunar calendar, releasing vast milky clouds of eggs and sperm on a schedule so precise, it's like a biological festival of mathematics. All of these rhythms, the daily, the monthly, the seasonal, layer on top of one another, creating a kind of biological calendar that every living thing on Earth follows. It's a quiet symphony, and we are all part of it, yawning in unison, waking with the sun,
drifting into sleep as the world around us darkens. And there is something deeply comforting in that, is there not? In knowing that your body is part of a larger, ancient rhythm, that while your own daily schedule might be full of meetings and traffic and alarms, underneath it all, a deeper, truer pattern is ticking along. A pattern shaped by planetary orbits, by ancient sunlight, and by the gentle gravitational pull of the moon. A pattern that whispers when it is time to rise, when it is time to eat, and when, at last, it is time to rest. And when you do finally rest, you are not just recharging your body. You are aligning. You are matching your own internal metronome to the great, slow rhythm of the earth, letting the mathematics of time carry you gently forward, one perfect, peaceful cycle at a time. Now, for a moment, let us close our eyes and simply listen. Not just to the loud, obvious sounds of the world around you, the distant traffic, the hum of an appliance, or the murmur of a television in another room. Try to listen past all of that, to the quieter, more subtle rhythms underneath. Perhaps you can hear the gentle call of a night bird drifting through an open window, the soft, sibilant hush of leaves moving in a gentle breeze. Or maybe, in your memory, you can conjure the distant rhythmic roll of waves upon a shore. These sounds are not just pleasant background noise. They are patterns. They are vibrations. They are quiet equations hidden in the very air around you. Sound is what happens when something moves and causes the air around it to vibrate in ripples. Those ripples, those invisible sound waves, travel to your ears where they are translated by the miraculous machinery of your inner ear and your brain into a rich symphony of meaning. Whether it is the sound of music, the warmth of a familiar voice, or the lonely croak of a single frog in the darkness, all of it is made of waves, tiny rhythmic compressions and expansions of molecules dancing through the air with astonishing precision. And these waves follow unwavering mathematical rules. The pitch, or the frequency of a sound, is determined by how fast the wave is oscillating. High-pitched sounds are made of fast, tightly packed waves. Low-pitched sounds are made of long, slow, gentle waves. And the amplitude, the height of the wave, is what controls its volume. Bigger waves mean louder sounds. When a musical instrument plays a note, it does not just vibrate at one single frequency. It also vibrates at a whole series of other, quieter, higher notes at the same time. These are called overtones or harmonics. These frequencies are always simple, whole number multiples of the main fundamental note. So when you hear a single note played on a piano, you are not just hearing that one frequency. You are hearing the main note accompanied by a whole choir of quieter, higher notes that give the sound its warmth, its richness, its character. It's these harmonics that allow us to tell the difference between a violin and a flute playing the exact same note. And nature understands this principle deeply, even if it does so unintentionally. Birdsong, for instance, is built on these complex harmonics. Many songbirds, like thrushes and warblers, produce sounds with incredibly rich and intricate harmonic structures. Their songs are not just for show. Birds use them to claim territory, to attract mates, and to communicate across vast distances. The mathematical structure of these songs is fascinating. Some species will even change their tune depending on their environment. In a dense forest, where high-frequency sounds are easily scattered by leaves and branches, birds will often use lower-pitched, slower songs that can travel better through the thick vegetation. In wide open spaces, high, fast, complex notes can carry much farther. It's a phenomenon known as acoustic adaptation, and it shows that even the forest itself has its own unwritten set of acoustical equations. And on a warm summer night, you might hear an entire chorus of frogs calling out across a dark pond. Each different species will be singing in a slightly different frequency range. This is not a coincidence. It is a brilliant strategy. If two species had identical calls, their signals would become muddled and confused. By separating their calls into distinct frequency bands, the frogs avoid this overlap and ensure that their own messages get through loud and clear. It is a kind of sonic social distancing enforced by evolution. And sound in nature does not only come from living things. The ocean has its own deep, resonant music. Stand near the shore and you will hear the rise and the fall of the waves, an eternal rhythm that is both beautifully chaotic and strangely peacefully consistent. The frequency and the amplitude of these waves follow mathematical principles, from the simple, gentle sine waves of a calm sea to the complex, powerful interference patterns of a great storm. And then there is the beautiful phenomenon of resonance. Imagine you are gently pushing a child on a swing. If you time your pushes to match the natural rhythm of the swing, it will go higher and higher with very little effort. That is resonance. Every object has a natural frequency at which it prefers to vibrate. This is part of how our own inner ears work. As we discovered in the spiral of the cochlea, thousands of tiny, delicate hairs are arranged along its length, and each one is tuned to resonate at a specific frequency, vibrating in perfect sympathy with the incoming sounds of the world. Your ear is, quite literally, a biological instrument tuned to the music of the universe. It is no wonder that certain sounds are so deeply soothing to us. The sounds of gentle rainfall, the wind moving through trees, the rhythmic crash and hiss of waves on a beach. These sounds tend to fall within frequency ranges that our brains find calming. They are usually low to mid frequencies, without any sharp, sudden, or high-pitched noises that might signal alarm. They mimic the peaceful, predictable rhythms of the natural world and of our own bodies at rest. There is a mathematical serenity to them. The ancient Greeks first discovered the deep connection between music and mathematics. The philosopher Pythagoras found that harmonious musical intervals, like octaves, fifths, and fourths, could all be expressed with simple, beautiful numerical ratios. This is why music is so often described as mathematics that you can hear. Every chord, every rhythm, every soaring harmony is a pattern, a wave, a frequency, dancing through time. And the natural world is full of this music, whether we are consciously listening or not. Great whales sing in low, resonant tones that can travel for hundreds of kilometers through the deep ocean water. Elephants communicate using infrasound, frequencies so low they are below the range of human hearing. Sound is not just a sense, it is a signal, it is a connection. It is a pattern passed through the air and the water and the wood, from one living thing to another. And the rules that shape these patterns, the wavelengths, the resonance, the harmonics, are all quietly, profoundly mathematical. It is comforting, in a way, to think of the world as always singing. Whether it is a blackbird at dawn or the soft hush of wind over the hills, the earth is never truly silent. It is humming, whispering, vibrating with the quiet equations of motion and energy. Not random, not chaotic, but beautifully ordered in a language made not of words, but of waves. And all we have to do is be still and listen. And so, as we draw this quiet journey to its final peaceful close, it is worth pausing for one last gentle breath. Together, we have wandered through the perfect spirals tucked into the heart of a sunflower. We have followed the fractal, branching paths of trees and rivers. We have listened to the hidden mathematics in the song of a bird and the rhythm of a breaking wave. And all along the way, one simple, profound truth has echoed softly beneath the surface. Nature is full of patterns, not rigid, mechanical, unfeeling ones, but living, breathing, elegant rhythms that whisper of structure, of balance, and of a deep and abiding beauty. The mathematics we have explored together tonight is not the kind that demands a calculator or lives only on a chalkboard. It is a math that lives in the delicate, six-sided way a snowflake forms, the way a honeybee builds a perfect, efficient home, the way your own body knows how to rest and how to wake with the slow, steady turning of the earth. It lives in the graceful curves of a seashell, in the patient, searching growth of roots deep beneath our feet, in the swirling collective dance of starlings, and in the ancient stillness of the mountains. What we find again and again is that the most breathtaking complexity does not require a complicated plan. Often, the most intricate and beautiful patterns emerge from the simplest rules, repeated with the patient grace of time, like a fern slowly unfurling, or a river choosing its most effortless path to the sea. In nature, order and chaos do not sit on opposite ends of a scale. They hold hands. They dance together. A murmuration of birds, a brewing thunderstorm, a perfectly timed and restorative nap. They all exist in that beautiful, liminal space where structure and spontaneity meet. Perhaps the greatest gift that the mathematics in nature gives us is the gentle invitation to slow down, to notice, to pay attention not just to the things we see, but to how they all fit together. The way the branches of one tree echo the branches of another, the quiet rhythm of your own footsteps on a forest trail, the soft, steady pulse of your own breath, quietly, faithfully keeping time. There is a deep poetry in it all, not just in the words that we speak, but in the shapes, the sounds, and the movements that nature writes across the entire world. And now, as your eyes grow heavier, or as your thoughts begin to wander gently somewhere else, let this be a soft and peaceful place for you to rest. Whether you are drifting off into a deep and peaceful sleep, or simply resting in this quiet stillness, know that the patterns are all around you and within you, steady, calming, and quietly carrying on. Before you go, if this gentle exploration has brought you a moment of wonder or a moment of rest, I would be so deeply grateful if you would give this video a like and consider subscribing to The Midnight Scientist. It helps others find their way to this quiet corner too, and it truly means the world to me. And I would love to know where in the world you are listening from and what time it is for you right now. It is always so beautiful to see how far these calm little ripples can reach. Until next time, sleep well, stay curious, and remember, there is a quiet and beautiful poetry in the patterns, if we only take the time to look.